C'est qui commence c'est tout ça juste pour voir si ça marche bien. Donc le laser marche bien et a priori le passage aussi. Je commence et je fais juste.
Okay, so hello everyone. This is the Lpwan working group meeting. You should all, of course, have read the note well, and have well noted that everything that you say and that you state here should be is public, and everything is recorded. And if you have any IPR on it, you should also say so. So minutes are taken, and this meeting is recorded, as we said. And you have all the necessary information on this slide. So we'd like to have some minute takers. So we have Dominique and people that will be joining. So you have the link that is on the Etherpad. You can use for remote participation, so the Meet Echo and the Jabber. Or so Scribe, Jabber Scribe. Who could do the Jabber Scribe?
Do we have a volunteer?
Yeah, thanks, Diego. So Diego will be the Jabber Scribe. So we move on with the agenda bashing. So today we have quite a full agenda, and we'll try to keep on time. Do you have any remarks on the agenda? Anything you would like to change?
Yes, Charlie's slide will actually be shared with Pat. So we have some additional slides from Pat about 15.4K. So that will be very, very interesting. So please stay with us.
Yeah. And before actually going to the presentation, just a short update of what's happening since the last meeting. So the working group has been formed in October. So we have two, just as a reminder, you have two main charter items. Produce a information document that actually documents and provides us the characteristics of our baseline technologies, and then provide the technology, the new compression mechanism for IP-UDP co-op over LPWAN networks. So this is like an extract of this. You should read the full charter if you want to know more. So we have a very tight schedule, and we're on time. So we've actually closed all the milestones that we have until now. And the coming milestones are so last call and actually moving and adopting work group, as with the work group last call of the Lpwan overview draft in April. Then the IP-UDP compression document in May, and the co-op compression in June. So normally we will have a pretty neat and a pretty lean system with everything out there for our next IETF, and we can do interop. And to mention this, so we had a design team that was announced on the mailing list, and all the nodes were also in the mailing list. This design team was formed around end of December and ran all until beginning of March. And it actually allowed to get all this work done. So everything now is on the mailing list. All the documents are out there. Please contribute. So we are moving on with our first presenter, Stephen.
Hi, so Stephen Farrell, that's the draft. There's a Git repo there. You can submit PRs if you want. Or I can do the next slide thing. So I'm the editor. Something's happening on your screen. Lots of people contributed. It's text from most people. Most of the text is not from me, but from this bunch of people. The content, it's just an introduction, kind of overviews of the four technologies that the working group has kind of started to look at. There's a bit of terminology, some gap analysis text that was contributed, security considerations, and there's the four technologies. So as I understand it, the goal here is to just provide enough background to be useful for, I guess, the IETF community, and not to kind of make this perfectly polished. Okay, so what's still to be done? I think it's, if we can make it shorter, I think that would be good. The technology descriptions, they need to be kind of checked and updated. I guess the working group last call or whatever. I don't know if more of the gap analysis work needs to be put in here or not. And the technology. So there's a couple of issues. Skip on to them. Okay, so first issue is basically just the descriptive material. There's a couple of individual drafts. So like we wrote a draft about the LoRa technology. I'm not clear entirely what the working group wants as to how much text they want in this document or versus those. So my assumption is, I think there's two options, and my assumption is basically number one. So that we don't try and keep it all up to the minute. We get corrections as we get them, but don't extract that text into their other IDs. So in the case of the LoRa one, for example, we might send that to the independent stream or something, and we won't, extract all the text from here that's overlapping with that. If anybody wants to go to the mic, then go to the mic if you want to disagree. Otherwise, I'll try and do what it says. Okay. There's a bit of generic terminology in there. To what extent do we want to be loosey-goosey with that, or do we want to develop a full architecture? I'm thinking number two. How many people have read this draft? Sorry. Okay. You're all in this corner. There was about 10 or 12 people maybe. So again, I don't think we want to develop a full architecture. The gap analysis. So I think there will be an issue here, is that there's probably some text in there that might end up in the standard strike document, or there could be some text in here that ends up in the standard strike document. So what do we want to do about that?
You mean about the parts, the gap analysis? Yeah. Oh yeah, of course. I mean, there are a lot of things that are happening on the gap analysis document, and then it will be up to you and the other authors to decide which parts go to the Lpwan overview document, if this is the question.
Steve, this is probably the only document of that family that will end up as an RFC.
Okay.
So anything useful should be in that one. That's for one thing. And for the second thing, the tenant of the various technology should really review the document, because we'll be aiming for last call. So what we'll be doing soon is ask for one reviewer from each of this technology to sign off and tell us that they're happy with the document, and then we can proceed with last call. Okay. But I perfectly agree with what you've written in the others.
Yeah, Sarah Krishnan. So I'll also like to go with one for reasons that you very well know.
Okay. So that's it. I think in terms of reading the content, I think the YSON description is lacking detail and references. The other ones I think probably can be relatively easily polished up to where we want them.
Well, we've got Bob Eiley in this room. I can see him. He's trying to hide, but he and so Bob, I'm sure you heard the message that there needs to be some polishing to be done on the YSON piece before it's ready to ship. So.
Well, yeah, I think we need some references to point at. I think that's the major gap. I think. So, so Bob's been committed to do it.
No.
And is the time frame the chair suggested of basically in the next month? Does that work okay?
That's really what we need, right?
So I heard a yes.
And then we'll also ask you to do this final review of see if you're happy with the whole document. Ideally, one per technology. So 4 reviewers.
Oh yeah, sure. The other ones, they're not finished, but this one is the one that's missing substantial things, which is the references really. And that's it. So if you any PRs I get, I'll send a mail to the list if there wasn't one sent to the list, and probably note them in the next draft of the document which ones were accepted. Any questions? Easy. Okay.
Move forward. Yeah, very fat agenda. So let's move. Thank you, Stephen. Thank you very much, Stephen. And with this, we call Alper. Alper, are you here?
Hello, everyone. My name is Alper again. I work for Actility. I'm also one of the 2 co-chairs of the LoRa Alliance Technical Committee. So in this draft, we briefly introduced the LoRaWAN, and I'll be talking about that. Both I and Stephen Farrell missed the previous IETF meeting, so that's why we're a bit late in presenting this. Otherwise, the draft has been around. So these are the general attributes of LoRaWAN. It operates in sub-gigahertz using ISM, meaning the unlicensed frequencies. It uses the LoRa modulation FSK with a channel bandwidth between 125 kilohertz and 500 kilohertz. And the data rates can be as low as 300 bits per second and as high as 50 kilobits per second. It has very high sensitivity, which provides a very long range, more than 10 kilometers, and also deep indoor coverage. The application payload size is between 11 bytes and 242 bytes. It's a variable MTU, depending on the data rate being used by the device at the time. And it has a very long battery lifetime, and the communication is a bidirectional unicast. Both uplink and downlink is supported, and also downlink multicast is supported by LoRaWAN. And LoRaWAN supports mobility, changing the network and moving around. And also it has a feature called geolocation. Without relying on GPS, by using triangulation, the network can determine the location of the device with certain granularity. And if we look at the network reference model, which is a very familiar picture, there's an end device using so-called radio gateways, which are in fact base stations. It is in touch with a so-called network server, and the LoRaWAN as a link layer runs between the end device and the network server. And we have a separate entity called a joint server. It's equivalent to a AAA server that's holding the root keys and performing authentication and authorization. And once the device joins the network, now it's ready to send and receive an application payload. And those payloads are exchanged between the end device and the so-called application server. The dotted interfaces are the ones that are currently out of scope for the LoRa Alliance, and the solid ones are in scope for the LoRa Alliance. And also the LoRaWAN specification you can download freely from the internet. You can see the link on this page. If we continue with the attributes, the topology we support is a star topology. We do not support mesh topology in LoRa Alliance. And each time device transmits an uplink frame, multiple gateways can receive those uplink frames. And that helps us with the gateway diversity, which is good for enhancing the coverage. And it also helps with triangulation with the geolocation feature. It also reduces the load on the gateways, and we can have a lower cost gateways efficiency. Efficiency is boosted by that stateless gateway approach. And also we have something called passive roaming. The device can be changing its gateway without really knowing what's happening. That is possible because gateways are not maintained in a state for the end device. On the downlink side, there's a single downlink transmission that is transmitted through the best gateway at that point. And LoRaWAN supports adaptive data rate. The transmission power and the transmission data rate of the end device can be controlled by the network. It's a dynamic parameter depending on the distance, depending on the proximity to the gateway. The device, if the device is closer to the gateway, it can reduce the transmission power, and also it can increase the data rate. And increasing the data rate is good because that reduces the so-called duty cycle, the amount of time spent in transmitting the data packet. And there's a limitation on that due to the ISM regulations. And if we look at the uplink and downlink transmission a little bit more, we support both confirmed and unconfirmed data. Confirmed data means there's an acknowledgement. Okay, these are two modes of operation for data packets. And also when transmitting an unconfirmed uplink, the end device can transmit multiple times the very same frame to increase the QoS, okay? And there's a frequency hopping at each transmission. The end device changes its frequency. That is to deal with, again, the ISM band regulations and also adapting to heavily used channels and all that. Due to the regulation, there are duty cycle limits, meaning that depending on your region, the device may be allowed to transmit only 1% of the time within an hour, or 0.1% of the time within an hour. That's duty cycle limitation. And also in certain regions like US, there's a dual time limitation. Within 20 seconds, the device can make one transmission and no longer than 400 milliseconds. These are the regulations related to using unlicensed bands. And there are 3 modes of operation that are supported, class A, B, and C. A LoRaWAN end device can transmit anytime, but for reception, we don't want to keep the device in the receiving mode all the time in order to preserve the battery. So in class A, the downlink is possible only immediately after the device transmits an uplink at well-known slots. That way, most of the time, that device can be sleeping, but then that device is best used as a sensor, not an actuator, and it would have a real long battery life. And in class B, the device wakes up at predetermined scheduled periods, and then you can be running that device as an actuator, still with an extended battery lifetime. And if you can keep that device always on, that requires it be a mains powered, then it's class C, so downlink can be sent at any time. So depending on your device and your application, you would pick one mode, and you can switch from one mode to the other. And there are a number of MEC commands we support in LoRaWAN. Some of them are used for checking the status of the device in terms of the link status, the battery, and the device margin, the signal-to-noise ratio as observed by the device. And also, a lot of radio parameters can be modified by the network server, such as the data rate, transmission power, transmit and receive channels, receive timing, how many times the unconfirmed uplink will be transmitted, and duty cycle and dwell time, which are regional parameters, can be set by the network on the device over the air. This is the frame format. I'm not going to go over it in detail, but what you should be aware is the application payload is carried in the so-called frame payload here, okay? And also the MEC commands, we are able to piggyback the MEC commands along with the data payload. And in order to do that, there's an frame options field here where we can stuff this field with MEC commands. And if there are no application payloads, these MEC commands we can also carry in the frame payload. So that's an optimization to be able to carry both MEC commands and application payloads at the same time. This is the stack. At the bottom is the LoRa as a physical layer. Above that, the link layer is LoRaWAN. And above that, right now, most of the deployments are using proprietary application stacks. And some of them are experimenting with using Zigbee stack, KNX application stack, Modbus, so on and so forth. So the outcome of the Lpwan working group would be to add IP to the top level here, riding right above the LoRaWAN link layer. In terms of identifiers, the end device has a long-term identifier called DevEUI. It's a 64-bit value, and it's generated based on IEEE OUI. And upon getting activated on a network, the network assigns the device a 32-bit ephemeral address, so-called dev-adder, and it's somewhat equal to having an IP address. The network server is identified by a net ID. It's a 24-bit value assigned by the LoRa Alliance. And the join server is identified by AppEUI, which is being renamed as Join EUI in the new release. And that's another 64-bit value, and it's based on IEEE OUI. And the application server is identified by ASID, which can be FQDN, IP address, etc. It's just a string. In terms of security, we use AES-128 cryptography in LoRa specification. Each device has a dedicated, and it has a dedicated 128-bit root key. It's called app key. And by using over-the-air activation, a dynamic join procedure, we generate session keys, one for network and one for application. And those session keys are used for per packet security. And those session keys also can be renewed, refreshed. The over-the-air data origin authentication, integrity protection, and replay protection are using AES CMAC. And the MEC commands can be optionally encrypted as well over the air by carrying them in the frame payload. Okay, when they are piggybacked, they are not encrypted. But when the deployment or the implementation cares about privacy of the MEC commands, they can do so by giving up on piggybacking and carrying the MEC commands in the application payload field, the frame payload field. And we also do end-to-end application payload encryption. So here we have the MIC, the 4-octet MIC field. This is what we encrypt the frame payload, and frame counter is used here for as a variance to provide a replay protection. And as for the ongoing developments, right now we are working on the backend interfaces specification. These are the interfaces between the AS, JS, and NS, and they are mainly used for join procedure or activation procedure and roaming procedures. And LoRaWAN specification we're also evolving. We're working on 1.1, which comes with additional roaming capabilities. Even with LoRaWAN 1.0, you can do roaming. There's one mode of operation available to LoRaWAN 1.0 family. And with 1.1, we're adding one more mode of operation for roaming. And there are security enhancements coming along with LoRaWAN 1.1. So that's what we have. Any questions, comments, Behçet? Hello, Behçet.
Let me be the first.
Yes.
Behçet Sarikaya here. Hello. Yeah, well, you talk about roaming. If it's going to be for refrigerator at home, why do you need roaming?
Well, when your refrigerator is stolen, we're going to track it. No, I mean, we also have, mobile devices. So we have mobile devices as well, like trackers, we put on packages and, yeah, your pet, etc. Yes. Okay, anything else? All right, thank you.
Okay. Thanks a lot, Alper. And our next presenter will be Carles. So Carles will be presenting the fragmentation piece of the SHIC work.
Okay, good afternoon. My name is Carlos Gomez. I am from UPC, and as Pascal said, I'm presenting the fragmentation part in the static context header compression document, also known as SHIC. And the other authors are also Anna Minaburo and Laurent Touten, although this is the product of the design team. So about the status of this part, fragmentation was added to the static context header compression document in version 0.1, and it was subsequently updated in version 0.2. And you may notice that this follows a quite different approach compared to that of previous individual submission drafts on fragmentation, because now this has been integrated with SHIC. Also, we've made an effort to allow for very short fragmentation header size, and also there's several reliability options enabled, as I'll explain next. So we have that some Lpwan technologies exhibit short layer 2 MTU sizes of even a few tens of bytes, a few hundreds. And for those, fragmentation support is mandatory in order to fulfill the IPv6 MTU requirement. And fragmentation will actually be used if, possibly after header compression, the IPv6 datagram doesn't fit a single layer 2 data unit. So in order to adapt for different scenarios and requirements for LPWAN deployments, this specification offers a gradation of fragment delivery reliability options, which are the following. First, there's an unreliable mode where the receiver does not provide any kind of feedback to the sender. Reliable per packet mode, where the receiver may provide feedback in terms of some acknowledgement after all the fragments carrying an IPv6 datagram have been sent. And then reliable per window mode, where the receiver may provide feedback after a window of fragments has been sent. A window of fragments is a subset of the whole set of fragments needed to carry an IPv6 datagram. So feedback can be also in terms of positive acknowledgement or negative acknowledgement-oriented behavior, meaning that an acknowledgement can be provided, reporting whether fragments were received or not, conditioned to whether losses have been detected. So it is important to note that the choice about which mode has to be used or the type of acknowledgement policy that is going to be used and whether this applies to all packets or not is not specified in this document. So the idea is that there will be further technology-specific profile documents which would state what is supported for each specific LP1 technology. Let's take a look at the fragmentation header formats. So we have a format for fragments which are not the last one, and then another one for the last fragment. So for fragments which are not the last, we have two fields. First is the rule ID, which was already defined in the SHIC document, which in this case is used to signal that the data unit being carried here is a fragment. And it can also be used to signal which of the reliability modes is in use. Then the second field is the compressed fragment number, CFN, which is a non-absolute fragment number. And this is set sequentially in a decreasing order. It starts from 2 to the n minus 2, where n is the size of this field, and it wraps from 0 back to the initial value. And later we'll see some examples on this. So for the last fragment, the CFN takes a special value, which is all bits set to 1, which indicates that this is the last fragment of an IPv6 packet. So also in the last fragment, we have an additional field, which is a message integrity code, MIC, which is computed by the sender over the whole IPv6 datagram before fragmentation. And then the receiver uses the MIC to perform an error check after reassembly. And it can also be used to elide the UDP checksum. So the algorithm used to compute this field is not specified currently in the document. And similarly to a previous comment, the specific sizes of the different fields R, N, and M, as you can see on the slide, are not given in this document. It would be stated possibly in this technology-specific profiles, although for N, which is the size of the compressed fragment number, we currently say that N has to be 1 for unreliable mode, because in that case, we don't need to identify different fragments because we will not have retries in this mode. And for the reliable modes, we recommend to use a value of N of at least 3 or greater than that, because we want to avoid a burst of 2 to the n minus 1 consecutive lost fragments, which would end up in ambiguity at the receiver side. So the receiver would still be able to detect that something has been lost, but would not be able to determine what exactly has been lost. So that would lead to resending the whole packet again, which is something we want to avoid. Okay, so let's take a look at the acknowledgement format. So it has two fields. First one is, again, the rule ID, which in this case is used to signal that this is an acknowledgement. And then there's a second field, which is the bitmap, that may be present or may not be present. If it is not present, it means that the acknowledgement is confirming the correct reception of all the fragments being covered by the acknowledgement. And otherwise, if there's some loss detected by the receiver, then this is indicated in the bitmap. So this means that the nth bit of the bitmap is set to 0 if the nth fragment transmitted has been lost, and the bit is set to 1 otherwise. So the remaining bits are set to 0 except for the last one, which is set to 1 if the last fragment has been correctly received. In that case, there's a signal by setting that last bit to 1. So you have an example here of a packet. Well, this would be the bitmap for the transmission of a packet that requires 11 fragments, and this bitmap signals that the 2nd and 9th fragments have been lost. So in this specification, we define a baseline mechanism. So a fragment receiver uses any layer 2 addresses present and also the rule ID to identify the fragments of a datagram. And it also uses the CFN and the order of arrival of the different fragments in order to determine the location of a fragment at the reassembly. So recall that we are dealing with star topology networks, so reordering is actually not expected here. Then, if reliable per window mode is being used, after the fragment with CFN set to 0, the receiver may provide feedback. CFN 0 indicates the last fragment of a window, and then the feedback can be made following a positive or negative acknowledgement approach. Then, when the receiver gets the last fragment, which is the one signaled by all CFN bits set to 1, the receiver uses the MIC to perform the integrity check, and then if unreliable mode is being used, if the check fails, then the datagram is discarded. If we use one of the reliable modes, the receiver may send an acknowledgement, then we can have the two options, positive or negative acknowledgements, and any lost fragments reported in a bitmap will be selectively resent by the sender. So actually there can be also a number of acknowledgement and retry rounds, and the maximum number of how many rounds are allowed is not specified in this document.
Carlos, you may say that basically the may in front of the ACK is really a mode where we do NAC as opposed of ACK, which leaves an ambiguity on the server. It never knows for sure if the packet was actually, well, the window was actually completely received or not, because either the last fragment was lost and there will not be an ACK, or the last fragment was received and all the fragments were received, which also turns out to be no ACK, right? So now this leaves this ambiguity if people decide not to do an ACK.
Yeah, so actually there's an item in the last slide about possibly adding a timer for the NAC, which we may talk about. Thanks. So, okay, here are some examples. I'm not sure if there will be time for all of them, but you have them in the document and in the slides.
Carlos, I think you have some time to go over, because I think this is very important that people have this understanding. So please take it.
Okay, thank you. So in all these examples, 11 fragments are required to carry an IPv6 datagram. So first we have this example of unreliable mode, where, as you may recall, n is set to 1. So here we only need to signal whether a fragment is the last one or not. And in this example, we are assuming that there are no losses. And that means that, okay, the receiver will perform the MIC check after all the fragments have been sent. And if there are no losses, then the datagram will be further processed. Okay, then let's talk about reliable per packet mode. And from now on, we will assume a value for n of 3. So this defines which is, well, the different values that will be used for the compressed fragment number. So as you can see, for example, on the left, the initial value for the compressed fragment number for the first fragment is 6. So that's the 2 to the n minus 2 I was mentioning before. And then the compressed fragment numbers are set sequentially in a decreasing order. So once the CFN reaches 0, then the sequence wraps again back to 6. And then we continue in this way. And the very last fragment, the last fragment of the whole packet, is set to CFN all ones, which in this case is represented as CFN equal to 7. So in the example we have here in this slide, we assume negative acknowledgement-oriented behavior. So on the left, we assume there are no losses. That means, okay, the receiver gets all the fragments, then because there is negative acknowledgement behavior here, there will not be this any kind of acknowledgement sent by the receiver. So the sender sees that there is no acknowledgement, so it just assumes that the transmission was correct. On the right, we have a similar example, although here we assume that some of the fragments have been lost. So what happens here is that, okay, after all the fragments have been sent, the receiver generates the acknowledgement, which incorporates the bitmap, which will tell which fragments have been correctly received and which have been lost. So this is only one acknowledgement in this case, after all the fragments carrying the IPv6 packet have been sent. And then after the sender receives the NAC, then the sender retransmits the lost fragments. So, by the way, in this example, we assume that after these retransmissions, there's no further problem. The retransmissions are successful, so there's not any other negative acknowledgement after this. So in this specific example, there's one problem, which is that, as you may note, the sender is using the same CFN for the fragments that have to be retransmitted, and this might lead to some possible ambiguity in some situations. So we already have a possible solution identified for this, which is called fragment renumbering. That means, okay, the sender knows which fragments have to be retransmitted. The receiver knows where they have to be located in the reassembly buffer. So instead of repeating the same fragment numbers, such as 4, 2, and 4 in the example at the end on the right, we could use 6, 5, and 4 to distinguish which are the different fragments being transmitted here. So we can also have the same approach, reliable per packet, but using a positive acknowledgement-oriented behavior. So in this case, regardless of whether there are losses or not, after all the fragments carrying an IPv6 datagram, then an acknowledgement is sent by the receiver. If there are no losses, such as on the left, then, okay, there's an acknowledgement without a bitmap to indicate that everything was correctly received. Otherwise, there will be this acknowledgement with the bitmap, which will tell which have been the lost fragments. And the difference is, in this case, after all the retransmitted fragments have been successfully transmitted, then there will be a final acknowledgement to further give a confirmation that everything has been finally correctly received.
Okay. Just a comment. We can have also an acknowledgement after CFN0 to say that we have received all the window.
Yeah, so that's
a window
here. Okay, so then as Laurent introduced, there's the other mode, which is reliable per window, where there's this option by which feedback can be provided at the end of each window. And the end of a window is signaled by the CFN set to 0 in this case, and also there's some last window, which is the remainder in the example. So we can have also negative and positive oriented acknowledgement behavior. So in this specific slide, we have the negative one. So if there are no losses, there is no NAC sent by the receiver, and the sender just assumes that the transmission was successful. If there are losses, then there will have to be a negative acknowledgement reporting which have been the lost fragments after CFN0. There will have to be retransmissions, and after each window, if all the fragments have finally been correctly received, there is no NAC. Otherwise, there will be further NACs. So this is negative acknowledgement behavior, and this would be positive acknowledgement behavior, where the acknowledgement is sent regardless of whether there are losses or not, in this case, after the end of the window. So after we have CFN set to 0, there's on the left, for example, an acknowledgement sent to confirm that everything was correctly received. There's a final acknowledgement sent after the last window, actually the last part of the packet, to say that everything was correctly received. And on the right, we have the same approach, however, with fragment losses. And in this case, the acknowledgement is sent after a window has been sent by the sender. However, it will report which have been the lost fragments happening in this example on the right. So these are the different modes and options that might be possible as per the current options allowed by the specification.
Carsten Bormann, you said the technology gets to choose one of these modes. I understand why it would choose unreliable mode. I understand why it would choose packet mode. what would be the reason to choose this third window reliability mode?
Okay, possibly my understanding is that it might help, it might be a way to avoid ambiguities without acknowledging what happens within a window.
Yeah, but wouldn't it be better to just fix the packet mode so there are no ambiguities?
Well, I don't know if...
I mean, this sounds a little bit penny wise and pound foolish. So you're sending all these X, which are really expensive, to save a few bits here and there. And where we can fix the packet mode so it is unambiguous, so we don't need the window mode.
Yeah, so actually, these were two different approaches that came up in the design team. So yeah, I guess we need to better analyze which might be the pros and cons in the lines of what you explained.
Ariel Montenegro. So I see that the normative language used is may. That implies you advise people not to send the X. Is that what you intend to do?
Well, what we need to make sure in the document is to explain that this is intended to enable two ways of giving feedback from the receiver. One is positive acknowledgement behavior by which always there will be an acknowledgement regardless of whether there are losses or not. And then negative acknowledgement behavior where some feedback is only provided if there have been losses in the transmissions. So I understand what you mean, and we need to make sure that the text actually reflects what I'm saying.
My question is it a may or a should? May implies you don't do it. A should it do it unless you really know what you're doing.
Yes, I guess the may is because you may have two options like positive or negative acknowledgement, but I agree that we need to clarify this.
Hi, Juan Carlos Zúñiga. Could you clarify whether you can change modes in the same session, or is it per packet?
I guess this is something to be determined by the specific technology profile, and I understand that within a packet it would be hard to change between modes, but maybe
from one packet to the other.
From one packet to the other, maybe you might be able to use different modes, and I guess this is up to the
implementation,
technology.
because some packets may require different treatment compared to others, or depending on the session. I don't know.
Yes. Yeah, if I can insist on something, if you compare what we're doing here with 6LoWPAN was mostly stateless and meant to serve in almost the same fashion all the various technologies, which had the price in the size of the headers that we are employing. Here we are serving different technologies which have different capabilities, different needs. So we had to provide a way to profile. So it might be that, yes, for a single technology, you may decide to go from a rule which says per packet to and define another rule which says unreliable. It's just two different rules. But you may also, for instance, if you have a standard body that says, oh, on my technology, I'm going to specify how I'm implementing SHIC. The group which decides that for the technology may say, oh, I may be using this mode like NAC or ACK, but not the other, right? Because my technology doesn't like to send positive ACKs, for instance.
One of our clarification is that we have the sender, as Alper said before, is not listening all the time. So we have to put some rendezvous point where we can wait for the acknowledgement, but not for each packet because it will consume too much energy.
Okay, so the last slide talks about things that we have identified that might be possible issues or things we need to discuss and possibly solve in the next revision of the document. So the first one is something I have already talked about, which is fragment renumbering for reliable per packet mode. The second one is that in reliable per window mode, we need to add a window bit to distinguish to which window a fragment belongs to. That's because there might be some specific situations where, depending on which losses happen, some ambiguity might arise. Then a third thing is that right now, there's nothing in the specification which triggers an ACK after the loss of a CFN0 or CFN01s. So possibly we want to add some timeout to trigger the NAC even if these losses happen. Then one other problem is that in some LP1 technologies, the layer 2 MTU may change over time. So we might find some problem if we first send a first round of fragments, and then what happens if maybe we have to retransmit some of them, but in the meantime, the MTU has changed to a smaller one. So, okay, this is something that we might handle. However, also it might add some complexity here. So we need to analyze if we really want to solve this problem or maybe adopt some simple solution like saying, okay, if this happens, the datagram is lost. So this is something that we might possibly discuss. And finally, something else we have talked about in the design team is that if we are sending fragments in the downlink, okay, we have that sometimes in many LP1 setups, we can only send something in the downlink if there has been some previous transmission in the uplink. So we might want to enable something to force the sender, well, the receiver in this case, to send something in the uplink if we want to send consecutive fragments in the downlink. So I guess this is the whole list of issues and things that we are considering and might need possibly some discussion to incorporate into the document. So any more comments or questions?
So you published the version with the fragmentation a couple of weeks ago, if I remember correctly. So I wanted to have a show of hands of how many people actually had the time and the opportunity to read this part. Okay, so quite a lot, at least around 10 people are there. So I think that right now that you need this feedback. So I would really like to see some people coming and reviewing the document for readability, for clarifying the points that Gabriel mentioned, you know, where there should be may, where there should be should. The team is there, they just need this input. And also for the questions that you asked, of course, they should be discussed on the mailing list. And it will be very useful to have the representatives of the baseline technologies to actually also provide some feedback to what should be really like very, very useful for each of these technologies, what could be less useful. So this way, you know, we can continue on the discussion, right?
Maybe I would like to modify my comment. Another viable alternative is to not use any normative language at all, because this is not meant to be normative. This is meant to be something to be profiled. The profiling documents will have normative language. And if you have it there, and if you have it here, and they conflict, which I guarantee will happen, then you know, you'll get into all these discussions. So if you have nothing here, and you always need a profile, it's very clear. That's a suggestion.
Okay, thanks.
Thank you very much, Carles. And Laurent, I think you're next. Oh, you're presenting. Okay.
Okay. Hello, everyone. My name is Sivayo Petrov from Axio. And as you might have noticed, today we are in Chicago, the chic city, or the city of static context header compression. So you might have noticed that this presentation had to be given by Anna Minaburo, but she couldn't make it, so I will fill in for her. So this is my first IETF presentation, so please keep that in mind. Okay, sorry, yeah. Yeah, I will try like that. Thank you. Okay. So I will start the presentation by giving you a little bit of overview how SHIC works and what's the general architecture, and then I will continue with providing details what was modified in the last version. So the difference between the previous version that was presented and the current one. So generally, we have a context that is shared between the end device and the receiver, the system. How do I, maybe, okay. So yeah, we have the same context between the two entities. And in the context, we have a set of rules that have some IDs. When we receive a packet that we want to compress, we try to match it against the rules that we have. And if some of the rules match, we send the rule ID plus any data that might be needed in order to decompress the packet at the other end. Then when the information is received, we get the same rule and we see how to decompress the information. So that was the very, very generic idea of SHIC. As you might have guessed, it's between MAC layer and IP layer. The idea is that, for example, when the end device wants to send some data, it compresses the IP packet and any upper layer information. And it sends over the radio only the compressed data, which is much smaller than the uncompressed one. Then the radio gateway receives this and handles it as normal. And it's forwarded to the network server. The network server knows that this device is speaking IP. So then it forwards the information to the compressor-decompressor, which in turn will decompress the information and send the packet over the internet. So now a little bit more in details how this whole thing works. An important part that I didn't mention earlier was how do we select the rules that match. So for this, we have a number of fields in the packet. And for each field, we have a matching operator and a target value. If the matching operator of the packet matches the target value in the packet, then we apply the compression-decompression function to retrieve the information that needs to be sent. There might be no information that needs to be sent. If the matching operator, for example, is equal and we have some target value. Or it could be matching operator most significant bits, let's say the 8 most significant bits from the UDP destination port. And in this case, we can send only the least significant bits from the UDP destination port. So now that I reminded you how the SHIC works, I can carry on to describe what was changed. So one of the important things that I want to emphasize is that the document that was presented before was just much more readable and things were added to it. It was not changed fundamentally. The meaning that was there was not changed. So thanks to the yeah. Anyway, so the most important things that were added was the fragmentation that we already saw and the matching list that was presented in different drafts. So the idea of the matching list is to have a very, if you have a very big space of possible values, but you are using just a very small number of them, to map them to some very short values so that you don't send that much information over the radio. So the other changes that were presented were the addition of the field ID. The idea there was that during implementations, people told us that this will be very useful thing to have, and it's much more concise than field name that was used in one of the versions of the draft. Another important change was that the fields must match exactly the fields in the packet. So the fields in the rules must match exactly the fields in the packet, because otherwise the decompression might get really tricky. And other important, not that, they're more like editorial changes, were the renaming of some matching operators and compression decompression functions. So here it's not really visible. There is a little bit of text over here, but it's not very important. So the matching operators that were defined before, they stay the same. They are not really changed, but we add this match mapping. The idea is that, for example, if we want to say IPv6 prefix, and we know that we will be only sending to one of 3 possible values, then we don't want to send the whole very long value. We map it to something much shorter, and we send this shorter value. So in order to know whether the field matches the packet, we compare the value from the packet with the long values from the rule. And if it's found there, then it's we accept that it matches. And in this case, when we need to send something, we send the short value. And on the decompressor side, when we see the short value, we just find it in the list, and we replace it with the long value. So I mentioned that some matching operators and some compression decompression functions were a little bit changed, but nothing really big. So there was a function named compute IP length and compute UDP length. They were replaced by the more generic compute length function. And similar things was done with compute checksum. So that's so. Thank you very much for your attention. If you have any questions, me and Anna Bro, who I believe is with us through Meiteco, we will be glad to answer.
Well, thank you very much. There again, we insist that it's quite different from 6LoWPAN, as you can see, because in 6LoWPAN, like I said earlier, it's mostly a stateful compression that we have that can be hard-coded in the device. Here we've got a context that needs to be installed in the decoding device. So when you have a network server, or you see it's not necessarily located in the network server, but when you have a location where this compression happens and you've got something to change, then the new format, you have to actually deploy that the context in that device is that it's able to compress and decompress.
Yes.
So it's a very different approach, much more stateful on the network.
Yes.
Which allows us to go as deep into the compression. Thank you. Thank you so much. Next is Laurent, I guess, for co-op.
Okay, so thank you, Doctor. So now I'm gonna talk about SHIC for co-op. So it's a very complex exercise because it's the first time we try to compress this kind of protocol with variable length for a lot of films. So what we have done first is to move all the functions, as Ivo said, from the co-op draft to the IPv6 draft. So this means that now we just define the behavior and not all these mechanism. So it's easier, but we will have to extend the functionality of this CDF compression decompression function and matching operator. We have also introduced, I will show it after, some directionality in the rules, so we can have uplink rules or downlink rules, and it's very, very efficient for compression. So what is different in CoAP from UDP and IPv6? First, we have some rule, for example, message ID. So it's the laser is which one? It's the red one. Okay. So here, for example, we have message ID. So message ID in the CoAP protocol has a fixed length of 16 bits. But in Lpwan network, maybe we will need very few of this value. So we have to find a way to compress this information. And the same thing for token. So we maybe have a very few values, so it's not useful to send a large token. So if the device, the thing, so I use the terminology in the overview draft is, so thing implement CoAP. So maybe the thing can select small value here and a token of 1 byte. But if the thing is a server, then the request will come from outside, and we cannot guarantee that the client outside will use small value. So what we have decided in the design team is to say that we can install a proxy. We will not say in this document how the proxy works, but this way we can reduce the value, for example, from 1234 to 00A, and same thing, the token can reduce from a 4-bit token, 4-byte token to 1-byte token. And after that, we can apply the compression rule we have defined in IPv6 context. For example, here, to use the most significant bit and say if the 12 first bit are equal to 0, then I will send only the last 4 bits. So this way we compress the message ID field, and we can do the same thing for the token, or in this example, we send 1 byte for the token. So it's a way to compress this value. Another big difference from IPv6 to CoAP is that in IPv6 or UDP, we have only one field with a name. In CoAP, we have options, and we can repeat an option several times. So for example, we have a URI path, and URI path can be a foo bar. So I will say in my context, I want to find foo in the URI, and I want to find bar. But if we just say that, then foo bar and bar foo will match the rule. So we have to say, for example, we want foo in the first position, and we want bar in the second position. So it's what we had in the matching operator. So in the matching operator, we will say, for example, foo has to be in the first position. So we have an equal here, but we look at the first position. So to be equal, it has to be in the first position, and to be equal here, it has to be in the second position. So this way we can have, we can compress a longer URI. The other thing that changed from UDP and IPv6 is that some fields have some variable length. And that will be a problem for deserialization, because if we don't know the length, then we cannot reconstruct the packet. So what we have decided to do, and maybe we have to make something more advanced, is that now we are sending directly the CoAP option. And in the CoAP option, we have the length. So this way we can do the deserialization very easily. So this is one possibility. Another possibility that is not discussed in the list is maybe to remove the option. So we have delta TLV. So just send the LV, but we break the alignment. So in my personal view, it's good because we want to optimize what we send in a link, but maybe it's not usually what we do. The last thing that is different and more complex to handle is that we have asymmetry. In IPv6 UDP, when you send something and you receive something, you have the same format. Here, when you send a request, you have, for example, your URI, but when you receive a response, you don't have URI, but you have other fields like content. So we have to find a way to match the rule. So it's what we have done by introducing a direction in the rule, and we say, for example, an entry in the rule is upstream, downstream, or bidirectional. So bidirectional is the default case. is what we find in IPv6 and UDP. And then matching operator will apply only for a direction. So we don't say which kind, it's on the rule that we will say if it's a client or the server, because we have different implementation, and sometimes the thing will be a client, sometimes the thing will be a server. So it allows us to define this kind of rules that are more complex, so to compress this exchange. So X, for example, version that we will find upstream and downstream, so we say it's bidirectional. Type will be said to be, so in the downstream, we expect to have a confirmable message, and in the upstream, we expect to have an acknowledgement or a reset. So this way, when we compress things in the downstream, we don't have to send this information, because we know that all the time in downstream, we have a confirmable message, and in upstream, we just send one bit that say if it's acknowledgement or reset. So here, the compression is not very high because we go from 2 bits to 1 bit, but it's very important to understand this, because when we have co-op, in one field, we have bidirectional, all the value bidirectional. Here, if we split the information in 2 parts, it means that we can send less information in all the direction. So it's optimized a lot of things. For example, we have the same example for the code value. So for the code value, for example, in that way, we expect just a get, so we can put just a get. Here I put a very simple example where I put only 404 and 205, but we can, so here it's 1 bit, but we can list all the error message we can expect from this application. So we can do the compression. Same thing for URI. We will have it only downstream, and content we'll have only upstream. So if we use these rules, then it's 36 bits downstream, and it's 14 bits upstream to compress co-op. This can be independent of UDP and IPv6, or this can be merged with rules from UDP and IPv6. So this way you have a very, very strong compression of this protocol. So that's what we have decided with the design team. So now we have to continue to work, and now it's go on the mailing list, so it's totally open. So we didn't discuss about other RFCs that use defined options. So we have observe. So observe is not that difficult. We just have to send the detailed TLV on the radio. And maybe we can install a proxy to reduce the size of the observed value to have something more compact. So it's something to discuss. Something that may be more tricky is about the block, because we can do the same way as observe. It means that just descend delta TLV of block and we send it on the radio. But we have already a problem, is that the smallest block is 16 bytes plus the co-op header, and we have some technology that allow 11 or 12 bytes. So it means that in that case, we have to put block fragmentation plus low-pan fragmentation. So the question is, do we do that? Or do we forget about block on Lp1 and we just rely on SHIC fragmentation for or Lp1 fragmentation for that? So that's an open question we have to discuss. Carsten?
Carsten Baumann, I think I can answer that question. You might use block to send a 5 megabyte firmware image. That won't be helped by LP1 fragmentation, so you need block. And the other observation is that the SHIC fragmentation probably is more efficient than block. So a combination of using block to break it down to manageable sizes like 100 bytes or 200 bytes or something, and then SHIC fragmentation in there is probably the best way.
Thank you. So that's one issue. The other one is that the rule is very strict. What we are doing now is very strict on the URI. So we say, for example, we have an URI with foo, bar, and a value. If we have something else, like foo, a value, and another value, it will be another rule. We don't have now the possibility to merge and say, we can have 2 elements in the URI and 2 elements, 1 or 2 elements in the value. So for me, it's not really a problem, because a rule takes a lot of, or takes memory, but if you have one rule and you add another rule, in the radio, it's only 1 bit. So having a lot of rules is not that expensive. It's a log of 2 of the number of rules. So it's not that important to increase the number of rules. But maybe it can be a problem in certain situations. So we have to study this. We have to study some platform like Comai, Lightweight M2M, or IOTVT, see how they manage to name their elements, their resources, and see if these things are working or not.
Suresh Krishnan, so you also have an equal without like a position, right?
We can have it, yes.
Okay. So that would like at least take care of the parameter things and the, right? So for the value, because value 2 and value 1 can be in whatever order, right? So we need to be able to match. Okay. So you need to have both position specific and
yes, but the problem is, for example, if I have just value and not value 2, then I will not apply this rule here because one value is missing. So one solution is to put 2 rules. Another solution is, for example, to create a null element. Let's say this rule, this emplacement doesn't exist. But if we do that, we go to more complexity on the serialization and deserialization. So
but if you say value is something equals, then both of them will match, right? So why would the presence of value 2 not match it? You mean like you're checking for both? So if you want to check for both, you have 1, and if you want to check for 1, you have 1, right?
Yes.
But the second rule will still match the value equal XXX, right?
Yeah.
Okay.
But if, for example, I have only a value XXX and not YY, so I cannot send it because the receiver doesn't know how many fields I have and will not be able to do the deserialization. So it means that here we need to create new element, a new way of serialization, deserialization, so it's more complexity and more bits on the radio. So before doing that, it's important to see if the current platform works with what we have defined or if we have to go further. So another element we didn't look at because we are not expert of this field. It's to see if we are not breaking the security, because the goal is to have end-to-end security even with compression. So we have to see with OSCOAP expert if there is some trouble in what we have designed. And the last point is about the timer values, because currently the COAP draft is working on high-speed network in the view of Lpwan. So here maybe it takes 1 day to send a packet or receive an acknowledgement. So we don't have and here we are very far away from these values. So I think we have to do more computation to understand this system. And this is very important because it will help us to design the size of what we are sending for the message ID and for the token.
This is the last slide?
Yes.
Okay. So Anna says that for both drafts, for this one and the one before, you need input from the mailing list, feedback also. And she says also that another question at the end, is it a need to have an IP, UDP, and COAP only compression, or we want to compress all the stack?
We can do both.
Okay.
So we can have rules for you. We can have COAP alone and use another technology to carry a compressed COAP. We can have COAP, UDP, and IPv6 in the same rule. It's very flexible.
Okay. Do you have a slide about the documents?
So I would also like to ask the COAP draft. It was also published quite recently. I might a month ago, something like this. The COAP.
Just before the deadline.
Just before the deadline, okay. And I get the impression that you have a lot of things there. And from what I read, is that so how many of you have read actually the draft? Had the time to read the draft? Okay. 7, 8 people, a little bit less than the IP draft, but I get the impression that it takes a lot of the principles that are the same here, and it works pretty well, and you are basically waiting for some input from some eventual deployment, but as it is, it works, right? So would it be, I think that this is a point that we could get some reviewers and to see also who would be interested in actually implementing this and running some real use cases to see, okay, how it, which of your questions and how they should be addressed. Yeah, okay. So let's formalize this as a question. Who would be interested in first reviewing this co-op draft, the co-op compression draft? Juan Carlos is one of the reviewers, and Michel Villet, and Karsten, of course. So we have three reviewers.
I have a question for Suresh here. So Suresh, you realize that the second draft co-op is quite simple. It is to the point. It's doing co-op, but the first draft is addressing pretty much the milestones that we had. But the milestone was saying, do IP, do UDP, do fragmentation. This draft and is very loaded, and plus the fact that it's actually the draft where we define all these techniques about rules, etc., which is generic and used by all the drafts. And we reach a point where reviewing that big draft will be difficult.
That's fine.
And
so just like do another milestone, right? Like we don't need reach order, just put a milestone I'll approve if you decide to go multiple drafts for the deliverable.
Yeah, and the question is, thanks, perfect. And the question is, do we split in two? Do we split in three? What would be the best? So for instance, should the basic...
So what would the third one be? So what would the third one be?
Well, the structure is like you've got this generic compression mechanism which says you've got rules and you've got those things, right? Then depending on that main abstract technique, you've got fragmentation, which use some rules. You've got co-op and you've got IP UDP. So it could be structured like 4. That's one way of structuring it. I don't know.
So, but that means like anybody who wants to do anything needs to implement at least 2 of these, right? Because they need to.
Well, the first one is not really. It's more like that's the technique. You don't implement anything by looking at it, but you know how to do things.
Just fold it into one of the documents, right? Take the technique, fold it into one of the documents, and just refer normatively to that from the other ones, right? Okay. So I don't want like something that's just like, hey, like, for lack of a better word, framework document, right? Because that's something like we've been kind of doing, like we do like a problem statement, requirement, use cases, like framework, architecture before we do any work. Like I just don't want to go in that direction. So like do one document, which has got the base stuff and like whatever is probably, let's say, most useful to implement, right? Like get that into one document and then get the other ones to refer to that and go on. So I don't mind more deliverables. I just don't want to like a deliverable which is not useful by itself.
So we'll split the fragment out of the IP UDP, and the general technique will stay with IP UDP, right? That's your recommendation. Yeah. Do you agree with that?
Not really. I prefer to have a document that describes how it works without telling if it's IPv6 co-op, but just give the functionality, fragmentation, and all the techniques for compressing. And then we can have a document to say how we apply it to IPv6 and UDP, and another document how we apply it to co-op.
So you would place the fragmentation with the framework, so we have at least something, and you would take IP and co-op separately. So it's more symmetrical in one way. But
yeah, but what will somebody do with that document, Laurent? That's my question. So like somebody reads that other document, right? It's just like it's like you're doing like a prior art search kind of thing, right? Like it's not useful by itself. That's why I don't want like a document which is just like, it's like writing a terminology document and things like that, right?
I agree.
Get to the mic, Kerry, so people.
Yeah, I completely agree. Just if I can express my opinion here, I like the way the current structure is, because it's straight to the point. We have a document that describes the current technology, the way everything works. It describes the way IP and UDP is compressed. So it's very specific. It shows how it works, and you have the framework there, and it's not that big. I mean, it's pretty reasonable. So it is useful. It is usable as it is. And then there is co-op, so you can profile if you want, and it doesn't add. I mean, it reuses all the techniques. So for me, for me, fragmentation is important part to see. So it will be something to see, but for me, I would keep it there as it is. So just keep it as it is. We are on track with our deliverables. Yeah, and then I mean, we could see afterwards, but as it is, it's okay for me.
Yeah, Carrie Lynn. If you split it the way Laurent proposed, and you move the co-op part to core, I would of course defer to the chair, the chairs of core, but it seems like you would get twice the number of reviewers. So that might be a benefit to do it.
So that's Christian. So like one of the things is like I kind of already promised that we'll review this in core when this is done. So at the BOF, like we already talked about like how we're going to review this. So but whether it's a working group document or not, like any cooperative stuff is probably going to go for review there. So I'll probably do like a last call on both the working groups. Like so that's not. So I really defer to you, but I just don't want a document which like it's not implementable and. Like so we said okay, like we'll have like one informational document that's not implementable, right? Like so for people to get some background of the stuff, and that's the overview document. So I just don't want another document like that. So I don't mind how you split it. I just don't want like an explosion of I don't know how to say this in a nice way, but I'm thinking of a good word, right? I would call it working group artifacts, which is not of archival value for people. I would like to minimize these kind of documents that are useful for the working group, but not after the work is done. So that's why I'd like, so if there's like one set of things where it's core for everybody, just get it done. So that's IPUDP. I think it's useful for everybody. And if you think, okay, maybe somebody might think like, I'm going to just do COAP without IPUDP, without even, I don't want to learn it, then it kind of makes sense to go your way where you split out the techniques first. But that's like far-fetched, I think. Like people who are going to read the COAP thing, they're probably going to do they're going to read about IPUDP as well, and they probably won't do it, maybe, right? Because for example, 3GPP might decide like they have their own techniques for IP and they don't know how to do anything more. So that's possible, but I don't think it's an unfair burden for them to make them read the IPUDP one as well. Maybe they'll get some concepts out of it as well. So that's why I want to keep them together.
Okay.
Juan Carlos Zúñiga, speaking in favor of this last proposal, I think one way forward, if I may suggest, is to keep in mind that split that you had, but still in the same document, clearly describe the mechanisms first, and then go to the implementation of IP and UDP in the same document. So that later on, let's say in the COAP, you can refer to that section that is kind of standalone, but still fits in a document.
We have right now.
So that I think would be clear. Perfect.
So. Yeah, maybe we can ask the room also or let's not ask the room, let's take the decision. Yeah, it is how. Yeah, you never. Okay. Yeah. Okay.
So now we have Thomas talking about an implementation of SHEC.
Okay, so hi everyone. My name is Tomas Lagos. I am an undergraduate student at the University Diego Portales, and I'm going to explain about my thesis work, that is the IPv6 implementation in LoRaWAN. So the objectives of this thesis, well, the principal one is implement IPv6. The other objective is reduce the IPv6 header and implement the neighbor discovery protocol in these networks. So how we start this project was we used the 6LoWPAN to reduce the IPv6 header, where the first 2 bytes correspond to the structure of the IPv6 header. And the best case that we get with using the 6LoWPAN was to reduce it in 4 bytes. So when the static context header compression came out, we decided to use it, but with the implementation that we have before, that is the 6LoWPAN. So, with the static, we make some functions with the static context header compression to compress and decompress the header of 6LoWPAN that is wrong, just because the static context header compression works with directly with the IPv6. So what we got with this project was to make a ping. So at the beginning, we make like a we make a IPv6 request that we convert it to to a 6-LoWPAN structure, and with that 6-LoWPAN structure, move it to a static context header compression ID. With that, we send that package to our LoRa gateway and send it to the nodes, the LoRa nodes that we have in the laboratory. And in the other side, to the node to the gateway, the node receives the buffer with the static context header compression, convert it to the 6-LoWPAN, and make a IPv6 reply, and do the same cycle that was doing before with the gateway. So with the accomplishments that we just make was they are using the link local address on the nodes and the gateway from the LoRa networks, make ISIN MPv6 request and reply, and use the static context header compression over the 6-LoWPAN. I just want to make it clear that in the future updates, we want to take out the 6-LoWPAN and use the static context header compression directly with the IPv6. And that is my presentation. Thank you. Any questions?
Thank you very much, Thomas.
Just a question, are you going to, your implementation, are you going to publish it somewhere? Is it available for?
Well, I have in the GitHub that I'm showing over there, I have the implementations that we make with the accomplishments that we have. So if you guys want to take a look about what we did, we'll be interested in that, your opinion, to keep this working going on. And yeah, super. Thank you.
Super, excellent. Thank you, Thomas. And Carlos, I think you're next.
Hi, everyone. My name is Juan Carlos Zúñiga. I'm with Sigfox, and I'm going to talk about an implementation also that we did, as Ivo mentioned, that we decided to call it Chicago because we thought it was a cool name and very timely. So this is over Sigfox, and it's joint work between our team in Sigfox and the team at Acleo. So Arun is not present here, but he is co-author here. So the demonstration is basically running the SHIC documentation that we just discussed about, the static context, IPv6 and co-op, running on top of the live Sigfox network here in Chicago. So we'll show this tomorrow, the bits and bytes live. And what we are going to be showing is two scenarios. The first one is the interoperability of this co-op UDP and IPv6 compression, running both over the Sigfox network and over cellular. So basically over Sigfox, we are doing the SHIC compression, and then we are communicating to co-op applications, one to the other. Over cellular, we are not doing the compression, and what we want to show is how they can seamlessly communicate without realizing which network they are working on. I'm going to show some slides about the details. Then for this, of course, we have a device that is multi-mode capable. It's a Raspberry Pi. The second scenario, though, is a legacy device, as we call it, or some dumb device that only has a microcontroller, so it has no IP stack implemented. And what we are doing there is we are directly reading from the compressed SHIC payload without necessarily decompressing it. So in this case, we are the same application on the cloud side is talking to this constrained device. The This is the setup that we'll have tomorrow. So, well, the displays you will see tomorrow. But on the Raspberry Pi, we have the co-op application. That's the smart device. This one here. And this is the dumb device that has no IP stack idea. So this one is capable of communicating both on the Sigfox live network here and on cellular back to the cloud application. The dumb device only talks Sigfox. Both devices, when they go over the Sigfox network, they use the SHIC compression. So they basically compress the co-op IP UDP, send it back to Sigfox, then they decompress it with the Aclio stack, send it back to the internet and to the co-op cloud application. This is the sequence diagram of what we are doing. So as you remember from the Sigfox presentations that I did in Berlin and Seoul, the communications in the Sigfox is pretty much like the class A that Alper just described for LoRa. So we have sensor based or sensor tailored network, mainly sending uplink communications, and downlink it's only on demand. So here we will have the co-op post value sending in this case the payload 64 that is being compressed here in the SHIC rule, and then decompressed back to the value. We are going to be sending a few messages. Then we want to send a downlink message that will change the configuration of the constrained device. Of course, that downlink message is not sent right away because it depends on, it waits for an uplink communication before sending. So it waits until the uplink communication arrives, at which point we can then reply with a downlink with a new configuration and then reconfigure the constrained device. So that's it. I encourage you guys to come and take a look at it tomorrow at the Bits and Bytes. And I don't know if you have any questions here or tomorrow. We'll be happy to answer.
I look forward, Juan Carlos. I do look forward. Okay, and next, Pat, that will be you. So we have inserted in the IEEE slot, we actually inserted a small presentation by Pat Kinney. And then Charlie will have the slot as expected.
I'm Pat Kinney, Kinney Consulting, and I'm just going to do two of these points up here, the 802.15.4K and 802.15.4G. Charlie Perkins is going to then do the interest group in detail. And let's see how that works. I'm skipping this part purposely. Okay, it's a lot of reading to do, but a long time ago, 15.4K was standardized, and its purpose is actually an LPWAN. We called it a low energy critical infrastructure for the application, but it addresses the application's needs of minimal network infrastructure, which is LPWAN. Obviously scheduled events from non-mains powered endpoints, widely dispersed, challenging propagation environments. A typical propagation environment for us is where it's very good when you install it, and then after 10 years, it's very noisy. So we needed that, the margin. And of course, in multi-year battery life, network maintenance, traffic, and wake durations. And then, as I mentioned, the changing propagation. It's star or extended star topology, asymmetric links, where the controller has more power, more computation ability. Same things that we've been hearing here. Yes, the frequency bands, all of those, there we go. Those were appropriate for us. There's two types of modulation. A direct sequence uses a code division multiple access with chip rates between 100 and 2,000 chips per second. And then the FSK is 12.5 to 37 kbits per second with spreading factors of 1 to 16. And then the maximum frame size for direct sequence is 16 to 32 octets. And then up to 2,000 octets for the FSK. Features, 5 fragmentation. The frame can be sent in less than 64 packets. The problem is, what we saw that the MAC header is too big to be sent in the smallest packet. So rather than try to reduce the functionality of the header, we just fragmented it into 5. And I haven't heard anybody else do that yet, but of course we do have MAC fragmentation, but here it's 5 so that we can have actually 6 LoPan all the way to the end device. There's no gateways. Transparent repeaters for range extension, no special configuration of the end devices. So the end device doesn't even know it's there. And then finally, both FSK and DSS use the forward error correction. Okay, this one's tough to read, and I apologize. 4G. 4G has actually been used by a number of other groups. YSUN is one of the major ones, but it's a very large-scale process applications, smart grid, okay? Large, geographically diverse with minimal infrastructure, so smart metering utilities. Here we go. Operation, I didn't want to list all the bands. It would take up all the space, but there's just a lot of frequency bands. 3 physical layers. You can have multi-regional frequency shift keying, OFDM, or offset QPSK. Data rates, 4.8 up to 400 kbits per second. Okay, achieve the optimal energy efficient link margin. Principally, it's outdoors. Again, 2047 octets is the maximum frame size. And then they designed it for 3 co-located orthogonal networks, and the connectivity, thousands, and then mechanisms for coexistence, and including 802.11. We have to prove that in to get this standard approved. Features, mesh. It focuses on mesh, channel hopping for coexistence and interference rejection, forward error correction, and then a common signaling mode so that all of the 802.15.4G devices can talk to each other and agree upon a certain frequency or so. So you'll see that 4G and 4K are complementary. If one's right, the other one, it really isn't, and vice versa. One's very slow data rates, but very long range. The other, with mesh, can get you the long range, but you're going to have more radios needed to relay the messages. Any questions on 4K or 4G? Thank you. Charlie.
Thanks very much, Charlie. Yeah, and we'll be really glad to see the K part going into the Stevens draft. Right. Thanks.
Thanks, Pat. So, let's see here. Oh, well. All right, good. All right, so this, I'm just going to go real briefly. There's more slides than really need to be presented here. Let's see if I go forward. Yep. And so I won't spend a lot of time, for instance, on this one. This is probably not too much new to say here, but I did include it for one reason, except for reference, if people want to look at the presentation. And secondly, to give you an idea of what we're actually talking about in the interest group. And so what the first thing I should tell you is an interest group is assembled in with 802.15 to see if there is interest to form some additional work. And the next thing that could happen is that we could form a study group which would study the issues to see if it's appropriate for forming an actual standard effort within 802.15, which would be a task group, or it could be that there's clear that we need to go directly to have a task group. So for this purpose, it's really a good idea if IETF LP WAN is aware of our efforts so that you can help us if you want, or at least be aware. And I think we should actually be collaborating in this effort. So again, very small power source and huge disparity between the number of aggregating nodes like base stations versus the sensor nodes. And another thing I want to mention briefly is that it could be that there's use cases, in fact, I think it's likely that there's use cases considered within this IETF working group that haven't really been considered within the IEEE interest group. But here's some kind of applications, and as you can see, they're mostly monitoring things. So, and here's the kind of LPWAN characteristics that we have. You can see there's, I think this is a pointer. No, this is a pointer. There you go. So this is what we think an LPWAN looks like, and we compare it against Wi-Fi. So in this comparison, Wi-Fi seems to be, you might say, too much for what people are looking for in an LPWAN. Battery lifetime of several years, I think, is very typical. Now, the next 3 slides after this are just a very small amount of looking into why the bit rates for LPWA are so small. And so I'm not going to go into that, but I'll just at least show them to you. And, oh, I should mention before anything else that Jorg Robert is actually the chair of the interest group, and he has been responsible for most of the content of these slides, like 85% or more. So I won't go through that, but it's not too difficult. And then here's a couple of graphs to show you the kind of path loss and so on that could be expected. And if you go through and plug in the numbers, you get the answers that you expect. So here's a couple of more things I want to focus on a little bit, which is that the base station can really detect a lot more data than the individual sensors can. So the idea is that we need to minimize the amount of work that has to be done by the sensors and still allow them to send up to the base station. All right, so in our model, at least, the acknowledgement is impractical because you have thousands or even millions of devices trying to send packets up to the base station, and if the base station had to send an acknowledgement back for each one of those, it's basically not going to work. And so that provides another way of understanding the strong asymmetry between uplink and downlink. And then for using TCP and IP, well, I don't have to go into this because we've been having a lot of good discussion about compression. And so I think compression and the gateways are going to be almost guaranteed. So this is an interesting look about the channel access model. If you look at that picture, what it says is, as time goes on, you have data being transmitted in your frequency band that seems to be not too much congestion or competition or interference, and suddenly you get zapped for a couple of seconds by some white noise, and so you can pretty much be guaranteed of losing data there and then going across here. So the intention of this is to show that we have to deal with complications in the channel, and there's a lot of Jorg Robert is referring to some research in low power wide area that actually should improve the channel access based on a LOA. So here's what we're doing. Given that view of low power wide area, we have a report due in July, and that's going to say, basically summarize the kind of work that's been done, and according to the use cases and regulatory aspects and channel models. So right now, what we're looking at is existing IEEE standards. And I should have mentioned that this is low power wide area for 802.15. This is an 802.15 interest group, and studying to see how well that fits the needs of low power wide area. Here's an example of evaluation technology. It's pretty much what you might expect. We take a look at the suitability, or the general suitability, and then break it down into individual pros and cons. And then if we have time, which we may not, try to get some exact information about how well the candidates compare to each other. So these are the parameters that are being used for the evaluation, interference, whether or not the nodes are mobile, and so on, or whether or not the technology allows for node mobile devices, and for instance, power supplies, and whether we need localization. So one candidate was looked at as DSSS, and so the result was if you need a large cell radius, maybe this is not the right technology. And so it's compared against all of these use cases of the kinds that we've mentioned before. So for access control and alarms and product production monitoring, the cell radiuses can be smaller. So then this is more suitable. But for public lighting or smart grid, it might not be suitable. So that's pretty much the content of what I had to say. The conclusion is that, or at least in our view of things, the low power wide area devices are suitable for monitoring, and the long range or wide area results almost inherently with low power and very low bit rates. IP overhead is too large, and so we'll undoubtedly have compression and so on. And so we are wrapping up. We'll be done in the summer. And if you have any inputs, if, for instance, you would like us to consider additional use cases other than what's been listed here, please feel free. So I guess that's it for my presentation.
Thank you very much. I have a question for both you and Pat. I don't know who will answer, but we do not officially work for something like 52.15.4K because it was not part of the original technology that we are considering. But is there some work like in this interest group to evaluate the applicability of what we are defining here to the various use cases in IEEE beyond YSUN, I mean, beyond 15.4G? And
I thought the initial focus, like Charlie mentioned, was really 4K and 4G to see, because really those are the two that come close to the mark, how well they perform. And where we go from there, actually, it hasn't been discussed, to be honest with you.
We see, on theory, a very great fit for 4K as well, right? The work we have here. But clearly, we can't add it to our charter. It's too late. But and we could not take so many. I mean, 4 was more than we thought we would take. But starting the work on 4K and evaluating SHIC on 4K, that would be very, very interesting.
Yeah, the sensitivity on 4K, I didn't mention it, but it's like -108 to -148. So it's right in the range. And so yeah, I'll put the information together so that it'll be available to this group.
Okay.
Okay, thank you.
So thank you very much. So yeah.
Let me just mention, I forgot to mention, if you look at our presentation, you get to find all these great pointers to more information. There's a lot there. So thank you.
Okay, thanks. And we have the last presentation. Are they publicly available? Are the documents publicly available, or are they available only to IEEE members?
All of the IEEE stuff is on this mentor system, and you can look, even just make a prefix there, and you can see all of the LPWA documents, all the 802.15 documents in general, and it's a gold mine of information.
Thanks. A quick update on the. Yeah, thanks, folks. A quick update on the LPWAN extensions. I think the chairs were curious on what potential extensions that we can bring to the working group. So let's look at few things. If you look at any of the LPWAN access architecture, fundamentally there's on the bottom layer there's a sensor cloud, and then there's the gateway which terminates the devices, MAC termination. The air interface, and then followed by a network server, which typically does the MAC termination, and also there's a element for radio resource management. And on the north of that is essentially an application server, or somewhere essentially your data resides in the topmost layer, right? On the left side, you have the policy interfaces. These are typically the LPWAN system architecture. You replace with LoRa with Sigfox or other access architectures, but
fundamentally it's the same thing, right? But what we have is the essentially, if you look at where the network server is, that is the intelligent element in the system. It is essentially doing the device onboarding, or essentially it's authorizing the device for the LoRa access. Now, essentially the gaps are essentially, if you look at it, there is the key gaps that we see are essentially there is no standardized interface between the gateway and the network server, right? Essentially, today what vendors do is vendors have their own agents which run on the gateways, and somehow those agents talk to the network server using a proprietary protocol. Now, if I'm a gateway vendor, if I want to talk to multiple network servers, I need to be able to, I need to allow them to load their agents on my gateway and have interworking with the network server. So this is potentially, this working group, IETF working group, can solve that problem by introducing a standardized interface, but essentially a standardized interface between the agent and the network server. That is one layer. And again, now from the LoRa point of view, to most part, the network server is where all the access related semantics terminate there, and anything on the north of that is only the data. It's essentially if you look at the IoT data management layer, it's all about data. There, I'm receiving data from the sensor devices. I put metadata, I have structured data, and allow applications to interface to my database, right? Now, there is a gap there again between the network server and the application server. There is no standardized interface, right? Essentially, like, the question is, can we do something here in IETF, right? So two interfaces, NS to gateway, NS to AS. Those are the two interfaces, right? And the third layer is essentially the radio resource management on the gateways, right? Now, like if you look at the Wi-Fi architectures today, we do quite a bit with respect to using a specific protocol. We use, fundamentally we manage various objects on the gateway. Now, ignoring the protocol, again, if I introduce LoRa access, still I want to be able to manage all those objects on the gateway, right? These objects could be potentially, if I classify them, it could be about radio configuration, it could be about per channel statistics, or gateway configuration, or device bindings, or broadly, these are, all the 5 classes, right? Now, within that, I can go, we don't have to review them here in detail, but pretty much, if you want to do radio configuration, let's say I'm deploying my gateways in the North American region, I want to make sure that the radios conform to the regulatory domain where of the domain, right? So that is one thing. Or I want to be able to say that, I have a channel policy where I want to enforce that channel policy on the gateways. Let's say my gateway is supporting 16 channels, and I want to, make sure that it's only operating on that, and essentially, push a policy to the gateway. Other things like, essentially power transmission, or any other, aspects, right? Again, some general statistics for management, right? What kind of, duty cycles or packet error rates or that I'm seeing. Other configuration aspects around, how I forward the data to the network server, or how I interface to multiple network server, right? And some other, bits and bytes. So essentially, like, again, going back, what in future we can bring is essentially, potentially we are looking at bringing this, work items to the group. That's it. Okay. Any questions, comments, let me know. Otherwise, thank you.
Okay, thank you.
So we'll be wrapping up. And is there any other business, anything that someone wants to tell us now before we adjourn? Okay, so you just saved 5 minutes of your life.
Yeah. Okay. Thank you very much.
Probably Steve at the very beginning.
Can you please tell us where the blue sheets are?
Everybody sign the blue sheet before you leave. Yeah, it will come back. It will come back here. Or if you don't mind, just go around and